Assalamu alaikum. Hello everyone. My name is Dr. Serine Soudani, Assistant Professor at Beji Mokhtar Annaba University, Department of Biology. Welcome to this presentation on Introduction to PCR and Primer Design. If you have any questions during the course, feel free to reach out to me by email, and you can also find my academic profile on ResearchGate for more information about my work. In this part of the course, we will focus on primer design. The main topics covered are the criteria for designing efficient primers, how to avoid secondary structures, the importance of melting temperature and annealing temperature, and finally, how to avoid repetitions and homologies. The summary will guide the rest of the presentation. In this session, we will focus on three main objectives. First, to identify the key parameters of primer design such as primer length, GC content, melting temperature, and stability at the 3' end. Second, to use bioinformatic tools to design and validate primers effectively. And third, to optimize PCR conditions by taking into account both specificity and the presence of secondary structures. By the end of this session, you should be able to apply these principles in practice when designing your own primers. So now, let's start with the criteria for designing efficient primers. When designing primers, several key criteria should be respected. Primers are usually between 18 and 22 base pairs long. Their melting temperature, or Tm, should be in the range of 52 to 58 degrees Celsius, with a GC content between 40 and 60%. It's also recommended to include a GC clamp at the 3' end. This means having one or more G or C nucleotides within the last 5 bases to ensure a strong and stable binding during PCR. Another important consideration in primer design is to avoid secondary structures, such as hairpins and dimers. For example, a hairpin with a delta G lower than -2 kilocalories per mole at the 3' end should be avoided because it destabilizes binding. Similarly, cross dimers or self-dimers should also be minimized, especially at the 3' end, since these structures can reduce PCR efficiency and lead to unwanted products. To reduce false priming and get enhanced stability, it's recommended to use primers with a less negative delta G at the 3' ends. In addition, avoiding repetitive sequences and cross homologies is also an important criterion, and we will discuss these points in more detail later in this video. In the second part of the course, we will see how to avoid secondary structures. Secondary structures in primers can interfere with PCR by preventing primers from binding correctly to the target DNA. To ensure efficient and specific amplification, primers must be carefully designed to avoid hairpins that formed when a primer folds back and binds to itself. It's particularly problematic if the loop is near the 3' end, and it should be avoided if the hairpin has a delta G lower than -2 kilocalories per mole at the 3' end. The self-dimers occur when two molecules of the same primer bind to each other, compete with the primer template binding, and waste reagents. It's acceptable only if the delta G is higher than -5 kilocalories per mole. And the cross dimers occur between forward and reverse primers. It can result in non-specific amplification or no product, and it should be avoided specifically at the 3' ends. How do we detect these structures? By using the IDT oligoanalyzer and NCBI primer blast. In the third part of this course, we will get to know better the melting temperature and the annealing temperature, and the difference between the two of them. The melting temperature and the annealing temperature are essential parameters for primer efficiency. Ideally, both primers in a pair should have similar Tm values to ensure synchronized binding. The Ta, which generally set a few degrees below the Tm, helps achieve high specificity during the annealing phase. Tm and Ta are critical because they determine how well and how specifically the primers bind to the template. If the aniline temperature is too low, primers can stick to the wrong places, causing non-specific amplification. If it's too high, the primers may not bind at all, and PCR won't work. That's why both primers should have similar TEM values so they anneal together at the right temperature, ensuring efficient and specific amplification. In the criteria of good primers, we talked about avoiding repetitions and homologies. In this part, we will talk about its consequences. So, primers should not contain repetitive sequences or regions that are too similar to other parts of the genome. Repetitive sequences may cause slippage during DNA synthesis, non-specific binding, or the formation of secondary structures. Homology with non-target sequences can lead to off-target amplification and even false positives in diagnostics application. To avoid this, always validate primer sequences using tools like BLAST to confirm their specificity. Finally, in this session, we covered the main principles, the design criteria, how to avoid secondary structures, the importance of melting and annealing temperatures, and the need to check for repetitions and homologies. Thank you for following this presentation on primer design. These guidelines are essential for designing efficient and specific primers, which are the foundation of successful PCR experiments. I encourage you to review the resources available on the platform and practice these concepts using the tools provided. If you have any questions, feel free to reach out to me by email, and I look forward to seeing your progress in this course.